This is my C# fundamentals tutorial, and I will be talking about a few different data structures: the stack, linked lists, and the tree. There are multiple data structures in C# and other languages. The stack and linked list and the tree actually, all these data structures are also in other languages, and so a lot of these same principles will carry over into other languages. The stack is a last and first out data structure. It allows you to push to the stack and then pop from the stack. So um, it allows you to, so whichever one you put in last will be the one that you take out. And so that's what the stack is. Um, there are a few different, uh, real world applications of this. This is a little example, as you can see here, of a stack and how to push and all those things. But anyway, this is the linked list. It is a linked set of nodes. So it's kind of like a linkage of lists. So like a group of data sets all linked together. And in this tutorial, I'm going to go over how to use it and what it is. This is a little example of the linked list and all that. Here is the tree. The tree is a hierarchical structure that allows you to put data under other data, and you can kind of build out a tree from there. As you can see here, this is an example of using a family member data program. So basically, you can get grandparents and then parents underneath of each of them, and then children. And you can kind of build out a tree, basically, off using the tree data set, the tree data structure. And we're going to jump into more depth about stacks. So this is the stack. This is my stack markdown for it. This is what I found pretty useful, pretty helpful. When you think about structures in programming, stacks are often one of the first structures introduced. A stack is a last in, first out data structure. This means the most recently added items the most recently added item is the first one, and it's also the one that's going to be removed. Stacks are useful in many scenarios, especially where the order of operations matter. The push and pop operations are kind of the backbone of a stack. So basically, you just create a new stack, and then you push to it all the different things you want in there. Integers, strings, all those things. Anything you want in there, you can put in there. And then you just pop it, and then you can see what the popped item is. Or you can even peek. So peeking is pretty useful. So instead of having to get rid of the item, you can just see what's at top. And so yeah. And so there are many real world use cases of this. Function calls, when a function is called or pushed. When the function finishes, its details are popped off the stack. An undo mechanism. Many software applications use stacks to implement the undo feature. Express evaluation stacks are used in parsing expressions, such as converting infix expressions to postfix expressions or evaluating postfix expressions. So basically, it's pretty useful for things that you want to make sure you get done. Here is another. This is the same example of the recipe, and then this right here is an example of taking characters and then pushing them back, popping them, and doing those things. So you can actually mess with characters and push them into a stack and use the stack to print out stuff. And then here is pretty useful. You can use a stack to actually make sure that you have the right number of parentheses in your expression. So say you have a pretty long expression, probably longer than this one, where you don't want to have to count and make sure that you have the correct number of parentheses around your problem to make sure it's balanced and you're not going to cause a problem. And this will do that. And for the problem to solve, this is going to be a challenge for anyone who wants to do it. You got to implement a stack that stores a sequence of recipe ingredients, create methods to add ingredients, remove the last ingredient, and display the current ingredient on top. This should define a recipe stack with methods to add, remove, and display ingredients. So this is kind of what your output should look like. I'm going to show you what the solution is. So skip forward if you don't want to see what the solution is, or pause it until you get it done, and I'll show you. So basically, it is right here, and it's pretty simple. You have three different little functions: add ingredient, remove ingredient, show top ingredient, and then this is your main. Boom. Boom. And then you just run it. And as you can see, boom, exact same thing that was in the challenge. All right, let's go back here. Stacks are a fundamental structure in computer science and are used in a wide variety of applications. Stacks are pretty useful. Definitely would recommend using them when they're necessary. All right, linked lists. Linked lists are also very useful. Linked lists are a fundamental concept often introduced early on. A linked list is a sequence of nodes where each node contains data and a reference to the next node. In this tutorial, we will use linked lists to store names, ages, and birth dates, and other things. Anyway, the nodes and references. In a linked list, each node is a fundamental unit that holds data and references to the next node. Understanding the structure of nodes and how they are linked together is crucial. The node structure, data, the information stored in each node, and then a reference, a pointer to the next node in the list. All right. So here, this is, as you can see, the structure of a linked list. So you've got your three different things that you want, and then you've got your node data point, and we'll show you like what node is the next node, and we'll point to them and create kind of a list of all these linked data data structures. And so here is how you can add and remove a node. So this is pretty simple how to add a node with the name, age, and birth date. Boom, boom, boom. Yeah, and you just run that and make sure you place it a name and an age and a birthday. And then to remove a node, it's slightly more complicated. You gotta go to the current head and then where the previous is null, and then you fall down and have a few more checks, and it will select that node and remove it. The traversal techniques right here. This is how you can go through the node, and we'll print off each node consecutively and go to the next node and show you all the data that is inside the list. So it has to iterate through each one. The use case, there are a few different use cases. Dynamic memory allocation. Linked lists can grow and shrink dynamically, which makes them useful in scenarios where the size of data structures is not known in advance. Efficient inserts / deletions. Unlike arrays, linked lists do not require shifting elements during insertions or deletions, making these operations more efficient. Implementation of other data structures. Linked lists are used as the foundation for implementing other data structures such as stacks, queues, and graphs. Example 1. So this is a linked list that allows you to have like a playlist of songs, for example. All right, and so you put in your title, your album, your artist, and it links it all together, and then puts it into kind of a playlist, and you add the songs, and then you can print your playlist, what your current playlist looks like after you put all your songs in there. So pretty interesting. And then this is another one. This is getting a data of a web page. You can add web pages to your data structure and print out what your whole long website could look like, data structurally wise. And then here is another example that I built out. This is a task. So for example, like you want to have a bunch of tasks that you need to get done, and you can have a task ID and a priority for each task, and add new tasks, and then you can say when you executed a task, and then go to the next task. The problem to solve, right? This is going to be the problem you need to fix, or the challenge, right? The same thing. You need to create a linked list that holds names, ages, birthdays, and implements methods to add new entries and display the list. First, create the node class with name, age, and birthday. Then create a linked list class with an add function and a print list function. You should try to make this project reproduce the following in the terminal. So this is what your main should look like, right? This you got to add and then print list to the linked list, right? And here are a couple random data, Alice and Bob. And your output should look exactly like this. Let me show you what that looks like. We'll pause it, right? If you want to do this on your own, and then we can come back. But I'm going to show you what it looks like and how to do it. So basically, print list, pretty simple, and add, boom, done. And then here's the data structure. This is how you build it out. Boop, 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 and boom, done. You just run it, and we get exactly like I said, like I showed. Cool. The last one, trees, right? Trees are pretty important. They are a hierarchy data structure. Trees are essential for organizing data in a hierarchy manner. A tree is a collection of nodes where each node contains data and a reference to child nodes, forming a parent-child relationship. In this tutorial, we explore the concept of trees, including their structure, traversal techniques, and real-world applications. Each node in a tree typically has two components, the data and the reference links to other child nodes, establishing the hierarchy, right? This is how a node can be defined in C#. And then this is what I built out, kind of like what it looks like, right? You have your top, and then you have your next layer, and you have your next layer of the tree. And the top node is normally called the root, and the child are called leaves, for example. And here are a few different traversal techniques. This is the depth first traversal, so this goes to the very end of your tree before backtracking. It goes to the farthest to get the data. And this is the breadth first, so basically you go through the first layer, all of the layers, all of the data in that first layer, and the second layer, and so on. And so this is how you add and remove nodes right here. This is adding, well, we kind of showed this earlier actually. This is how you add the child node. And then this is how you remove a node. Pretty simple. You just pass in that name right there. And then the real world application. So hierarchical structures like the tree is very useful in file systems, organizational charts, and decision trees. Here is an example of a file system. You have the root, and then you add the folders to that root, and then you add the files to the folders. And then you can print your tree. Here's the family member thing, right? You have your root, then you add your parents, then you add your children. And so, yeah, pretty simple. Then you have your, this is a decision tree. It's used for AI. I'm a big AI guy, but this wouldn't create any type of AI. But this is a decision tree is one of the many algorithms that AI can use. But anyway, here is the root. You add a yes, no, or a node, the yes node or no node, a yes umbrella node, and so on. So it kind of builds out this tree, a decision tree. And so here's your problem to solve. Here's the challenge, right? After I read this, pause it before going on so that you can make this yourself. All right, so you have to create a tree that represents a university department hierarchy. The hierarchy should include department heads, professors, courses, and students, and each of those under each other. This is the structure. I have the structure right here for you that you can build off of, and then this should be your main, right? Adding the professor, add. So you add the students, add courses, add professors, add all those things. And your output should look like this, right? You have the university at the top, boom. Then you have university head, professor, course, student, right? And that's what it should look like. And so then we go to here, and I'm going to run it for you. This is what it looks like. Oh yeah, you should have paused it, by the way. You can still pause it because it's pause it if you want to do it yourself. This right here is the university node, the university tree, right? Add professor, add course, add student, and this is if you want to. You don't have to make this right here. This is the find node, and then print tree, and then print tree, boom, and that should create it for you. Run it. Boom, exactly like I was saying. There we go. Prints out the whole thing for you. Shows the tree. All right. That should be all of the different data structures I want to go through today. If you have any questions, right, go to the outline right here. Email me. Hit me up with any questions you have. Thank you for watching my video.